Epsilon-proteobacteria seem to fall into two phenotypic groups. The ones you think of, or maybe know a little bit about, are the gut symbionts. So Campylobacter, Wollenella, Helicobacter are in this group. Most of you probably, well, I should say most of you, a pretty significant fraction of you probably have Helicobacter in your stomach. I know I do. It's a common symbiont in the stomach. In some people, it causes gastritis, or worse, stomach ulcers, and are also can ultimately lead as a result to stomach cancer. In most people, they're probably benign or even beneficial because people who don't have Helicobacter in their stomach are more susceptible to acid reflux. And so the good news is prevention of acid reflux. The bad news is potentially gastritis and stomach ulcers. And why some people are affected one way and others the other is, as far as I know, unclear. Most of the organisms in this group, though, and certainly in the environment, the most prevalent ones, are the sulfur oxidizers. These are organisms that are really, really common in ocean sediments. And these Epsilon-proteobacteria are major components of the ocean sediments. And you're talking about a huge environment here, right? This thing is just not going to be consistent today. So here's Helicobacter pylori, the one that most of us have in our stomach. It's a curved rod. It's a heterotroph. It's got some interesting hydrogen metabolism that deals with how it survives in such an acidic environment in your stomach. The diagnostic feature of it is that its flagella, which are polar, don't actually protrude from the outer membrane, but they're surrounded by outer membrane. And at the very end, there's a little bulb. I guess you would have to say that that's periplasm in that little bulb. The sulfur metabolizers, again, they're quite common in the environment. There are some of them that are symbionts of this thing. We may talk about one of these papers before the end of the semester. It's really cool. This is the deep sea hydrothermal scaly snail. So it's got no operculum. That's the thing that's on the other side of the shell that closes up behind it. Instead, it has these scales. And these scales are covered in armor, iron sulfides. It prevents predation, right? They can pull the foot in and present those scales to the predator, and they're metal coated. This animal doesn't eat. It has a radulus, a tongue that most snails use to scrape with, but it's vestigial. It can't even protrude out of the mouth. It has an intestinal tract, which is empty. So how does it survive? The foot of this animal is highly vascularized and absorbs oxygen and CO2, ammonia, and hydrogen sulfide from the environment. So it takes all these gases in, and those gases are transmitted by the vasculature to the esophageal gland. The one thing in the gastrointestinal tract that isn't vestigial, in fact, is highly enlarged. And the cells in the esophageal glands are the glands that secrete lubricant into your esophagus so you can swallow things. The esophageal glands are full of bacteria. And these are intracellular parasites, and those bacteria oxidize that sulfide and make energy. There are also autotrophs that fix CO2, and they fix nitrogen. And all of those things are provided to the animal in return for a place to be. And so this is, in a very real sense, an autotrophic animal. Just like the deep sea hydrothermal vent tube worms, Riftia, and the clams like Calyptogena. These are animals that form symbiosis with these autotrophic bacteria, and provide the animal with what it needs. There are also Epsilon-proteobacteria that probably help provide this armor plating. Oh, and I didn't mention, it's an Epsilon-proteo that is providing this animal with its resources. Probably also the biofilm on these scales and the production of those metal plating is carried out by Epsilon-proteobacteria. And there are also some on the outside, although the blackness of the shell is just a pigment, just like any other snail. It's not iron sulfide.